how small can you possibly imagine? Millimeters, nanometers, maybe attometers. How about the Planck length? But can you ever just imagine a true zero? An absolute void that's so small that it might actually just contain everything. Relax as we embark on this journey, traveling from what we know to what we can't even imagine, in a journey through the quantum realm. Rulers or scales generally come with demarcations as small as 1 millimeter. That's about the thickness of a plastic ID card. But human eyes can generally make out objects with thicknesses 1/10 the size of a millimeter. That's about the thickness of a sheet of paper. Yet, humans weren't satisfied. We began developing tools to magnify smaller objects, enabling us to see them. Using lenses, we could bend the path of light in ways to make objects seem larger. The simplest arrangements started off with a single lens, forming the magnifying glass. But this quickly evolved into more complicated arrangements of lenses, forming microscopes. Using these microscopes, we could manipulate the arrangements of lenses as we pleased to see smaller and smaller objects. We saw cells, cell organelles, material surfaces, bacteria, and so on. But then we hit a fundamental limit. In order to see objects, light has to bounce off of them. This light comes in different wavelengths that correspond to different colors. These wavelengths have to be smaller than the objects in order for reliable reflections to occur, allowing the objects to be seen. As visible light is around 380 to 700 nanometers, we can't possibly see anything smaller than this, no matter how much we magnify. Realistically, anything smaller than 500 nanometer just can't be seen this way. Yet, that didn't stop us from inventing other methods for visualizing things far, far smaller. Just as light has wave-like properties, other quantum objects also have wave-like properties which can be detected by other instruments. By using electrons to bounce off of objects, we invented the electron microscope. Here, the electrons bounce off of objects and are then sensed by specialized detectors instead of light. Using this method, we can see things like viruses and even individual molecules. That's the same as taking 1 millimeter and dividing it into 10 million parts. Even though we can't see anything smaller, math and physics allows us to describe things much, much smaller than that. However, the descriptions would not match what we'd actually see in most scenarios owing to the effects of quantum mechanics. Even then, talking about sight itself becomes somewhat ambiguous as things simply can't be seen. However, let's dive further with the assumption that we're shrinking in a way that allows us to have a new form of sight that doesn't use traditional light, allowing us to see no matter how small the objects become. Right now, we're at the size of atoms. Most high school atoms are depicted as such, which we learned to be mostly incorrect as we go into higher studies, where we learned that electrons exist as probability clouds and atoms would look more like this. Yet, if we were to shrink down to that level, since we're observing the electrons at all points in time, they would actually exist in only one place at a time, and hence would look a lot like the high school depictions, with every electron present as a single particle, moving around the minuscule nucleus. These electrons wouldn't be moving around in a classical sense of movement, but instead would be teleporting and jumping around here and there, making it seem like a world of chaos. However, chances are that we'd never actually be able to see an electron simply because they're too small, even at these scales that we're in. We know that if electrons do have a size, they're definitely smaller than 10 to the power minus 18 meters, which is about 100 million times smaller than where we're currently at. So realistically speaking, at this scale, we might just be seeing a complete void. We'd be at the size of atoms, but the electrons and nuclei would be vanishingly small. Now, shrinking down by another 10,000 times, we'd reach the order of about 10 to the power minus 15 meters. Here, we'd reach the nucleus. Protons and neutrons be vibrating vigorously, energized by the will to explode due to the electrostatic repulsion, yet constrained by the strong nuclear forces. A very dynamic world, isolated by large distances. With the right tools and developments in science and technology, it may one day be possible to obtain a real-time visualization of individual protons and neutrons. Will we ever succeed? I don't know, but the possibilities do remain. Protons and neutrons are made up of quarks. These are theorized to be 1,000 times smaller than protons and neutrons. They're on the order of attometers. That's 10 to the power minus 18 meters, which is the upper bound of the possible size of electrons. Even though we know these particles exist and have detected them, real-time visualization of just these particles may never be possible, as isolated quarks can never exist. They will always be found in hadrons like protons and neutrons, or else in mesons formed by quark-antiquark pairs. This is due to the properties of quantum chromodynamics. However, nothing stops us from imagining what these would look like down at these distances. We could imagine these objects to be spheres very similar to that of protons and neutrons, just far smaller. However, being fundamental particles, they might not have a size or volume as such. Based on different theories, their shapes and methods of existence would change. Quantum mechanics would imagine them to be particles, while quantum field theory would simply equate them to a disturbance in a quantum field, hence implying that they have no physical form to be seen. Other theories like string theory would consider them as strings vibrating in various more spatial dimensions apart from our own three. We know that our theories are not yet complete or absolute until we figure out the true theory of everything, determining the true nature of these fundamental particles. We're only limited to our own beliefs and imagination. Our biases sometimes correlate mass with size, assuming that objects with greater masses must be larger than ones with lower mass. We now know that the mass of these fundamental particles are determined by their interaction with the Higgs field and hence should not necessarily correlate with size, but that assumption would make things easier to imagine as we go even smaller. The lightest things we know of till date are neutrinos. We know that they must also be very, very small, as billions pass through you every second. but only a handful will ever actually interact with an atom in your body in your entire lifetime. These would form the smallest objects that we know to exist for sure, and are probably on the order of 10 to the power of minus 24 meters, which is yoctometers. That's a million times smaller than a quark. However, for all we know, quarks and leptons like electrons and neutrinos are point objects with no shape and no volume. But still, they have the power to combine together and form everything we see in the known universe. The smallest theoretical objects, however, are strings from the string theory. These strings would be in the order of the Planck length, which is about 10 to the power of minus 35 meters. This is like 100 billion times smaller than neutrinos. If these strings exist and we could see them, they would look nothing like vibrating strings, as they'd be vibrating in far more than 3 spatial dimensions. This would give them a weird kind of motion and possibly a weird shape that would keep changing as time progressed and as they moved through the various dimensions. These strings would literally be hyper shapes that our brains just aren't designed to truly comprehend. However, at that scale, even we'd gain access to those higher dimensions, making everything seem psychedelic, an experience that our minds may never grasp. Even though we can never imagine what being this size may feel like, we at least made it down to the smallest possible size that our universe has to offer. The Planck length defines the smallest unit of space. A Planck cube, which is a cube made of sides of lengths of 1 Planck unit, is the smallest possible volume that can ever exist in our universe, much like a single pixel on our screens. And with that, we'd have to end our known journey and tread into an impossible journey that not even science fiction can predict. The start of this documentary stated that a journey to size 0 might take us through a void so small that it might actually contain everything. Apart from trying to be a clickbaity hook, traveling smaller than the Planck length could actually be weirder than the psychedelic experience we'd face with the strings. It definitely isn't possible, so the following statements are more of opinion than scientific fact. But being within a single Planck volume and shrinking would break reality. If you were to go down that small, you would no longer be bound to the laws of the universe that we know of. However, you would still have to be bound to some laws. Those new laws might just be the governing laws of a whole different universe, a mystifying place with an uncanny familiarity, a universe whose occupants know the Planck length to be the border of their reality, a cosmic horizon that they'll never reach. Your journey restarts as you slowly continue shrinking down through their universe, all the way to their universe's Planck length, which just takes you back to a never-ending cycle for eternity, as your distance continues to drop with more zeros after the decimal point before the 1, but never quite enough zeros to reach true, absolute 0. Writing the script for this video was a blast, and I hope it unlocked your imagination and gave you a ride through the known into the unknown in a way you've never experienced before, allowing you to question things you never questioned till now. I'd love to hear your feedback, and I have a lot more coming up. So stay tuned and subscribe if you feel like you'd enjoy this form of content. Thanks for watching. Stay safe, stay curious, and keep learning.